Moving on. So this is just the next strip for 9.1, and we're doing every time. Let's keep in mind that we're going to, for these whole sets of gluons for 9 and 10, we're going to follow the electron. That's the best way to think about this as far as what's going on, because that electron would be sourced from a bond, and when you have a bond that's broken, there's two main processes going on. One is this rearrangement of the atoms in the molecule into a more stable state, which will release some bond energy that's usable, but it also has electrons that came from that bond that have to be transferred, and they have energy that is not useful. It's not manageable. It's serial killer extreme. So you're going to have some process in place, which is what we talked about here, where the electron in its high energy state is going to be passed from molecule to molecule, and these molecules have the job of holding those electrons. And as they do, they hold them in such a way where that electron will drop stepwise in energy. So you end up with, we can put it down here now, so here's a different way to look at it, energy level wise. You've got this electron, and every time it's given to an acceptor, it's going to lose energy, and this right here, this amount of energy here, this drop, is going to be the energy that is a good, normal, manageable amount. It's a little dab of toothpaste. It's the energy that can be used to do work. So now the energy's in, the electron's in a lower, gets passed again, it goes to a lower, it gets passed again, and then it's finally in a low enough state that you can't go directly from there to there. It has to be this passage sequential. Okay, so that's just a reminder, because this question starts off with it. Hey, cats break things, so when we're talking about breaking bonds and they're in a pathway, these aren't going to release energy that can be used directly to do cellular work. So you're not going to couple the fact that you broke a bond with needing to have a motor protein carry an organelle along the cytoskeleton in the cell. You can't do that. You're going to have to create a system of converting energy into usable forms. So just something to think about. If you think about energy as money, often what you're getting from these bond breaking is you're getting these big bills. So you get something like a $100 bill. And cells don't give change. So it's an all or nothing use of energy. So it has to be in the appropriate amount. So a silly example would be if you wanted to buy a $1 candy bar, your choice would be to give $100 and just give up the 99. Cells can't live doing that. You can't. So you do not use the $100 bill. You have to figure out a way to get this in a form that's usable. So the way this works is it's going to have to be, because this is a pathway. So what this is, so this is just a silly example. The real answer is that you allow the bond breaking, so that bond breaking where you're rearranging those atoms into a different configuration that's more stable and therefore has released some energy. So you allow that bond breaking to be part of just a system with steps, to be part of a system with steps. And that way you can manage that energy. So you couple, what this is meaning is that you couple the reactions. So a reaction that has a considerable release of energy would be coupled with a reaction that required a considerable amount. And so there's just this partnering to where that you're able to exploit that in little steps, one piece at a time. So redox is really important. It's a combination. This is 5. Redox is really like a made-up combination word. It's 2 parts. The ox part is oxidation. The re part is reduction. And here's what we're demonstrating by putting those together. There's always going to be an oxidation and a reduction together. And let's talk about what those are. So the word itself, reduction, if you do the verb, reduced, so let's put a buzzword under that because that's a word we're going to use all the time. Reduced refers to the molecule that gained or accepted the electron. Because whenever there's an electron that's going to be released, there has to be some molecule that takes that electron. They're never set loose. So if you have an electron that's going to be lost, is what they'll call it. That's what oxidized means, is that's the molecule that lost, so loss of electron. That's the molecule that lost it, so we call it oxidized, but it's never just, well, I lost my electron. Something took it, and so it's reduced. So these always go together. So where you have bonds being broken, and there will be a release of a transfer of an electron, whatever that electron came out of, whatever lost it, is oxidized, and then it was accepted, the electron was accepted by another molecule, and that molecule was then reduced. So the only reason we have this little thing down here is to help us remember what this means. So oil rig is oxidation is loss, oil, reduction is gain, rig. It's just a way to remember, and I think y'all had like Leo the Lion Goes Grr or something like that in chemistry, but oil rig makes more sense to my head. Oxidation is loss, reduction is gain. We're talking about electrons. So it helps to put this in perspective for a real pathway, a real process. So instead of writing this short paragraph, we're going to use these words right here to make sure we know what those are, but we're going to do it in context of a true pathway example. So if you think about what we've done so far, we've said what reduction is, that's gaining an electron. We've said what oxidation is, that's losing an electron. We'll come back to these oxidizing, reducing agents. We've said what reduced is, oxidized, loss, and gain. So we're mostly there. We'll add these in just a minute as definitions. But I want to give an example of how this works. And we're going to go back to glucose because the whole chapter is oxidation of glucose. Oxidation means you're breaking bonds that cause electrons to be released when they're released, they're lost. That's what oxidation is. So if we start off with glucose, which we know has 6 carbons, and so the goal is to break it into 1 carbon pieces. So you've got carbon dioxide. So you're wanting to snap all those carbon-carbon bonds until you have nothing but carbon dioxide and water left. So the way this works is, for glucose, the job of the process is to break these bonds, but not all of them. You don't just poof, break all the carbons apart. You're going to break the bonds one at a time. So it's part of this sequential pathway where you have enzymes that change or contort the molecule in such ways that, because those bonds are weak and unstable, they move to a formation or a conformation of a molecule that is a better energy state. It's more stable. And then you release some of that energy that was there between the difference of weaker bonds, unstable bonds, to becoming stronger, more stable. So when you do this breaking of bonds right here, you're going to generate, so this creates, when you break your bond, it's going to create 2 electrons, and where electrons go, hydrogens go. So you're now stuck with electron management. What are you going to do? So the way this works is these are going to be passed off to 2 different processes. So the electrons themselves have to be given to an electron acceptor, an electron carrier. So they're going to, these 2 electrons are going to be given to a molecule called NAD. And when it's in its I can accept electrons form, I call that an empty bus. So think of it like a bus with 2 seats. NAD is the empty bus. When you put the electrons on, 1 hydrogen goes with it, and what you form is a molecule that's called, you can guess now, NADH, because the H is now going to be part of this. This is the full bus. NADH has received electrons, and both of its seats are full. The bus is full. So now it's going to be able, because it's an electron carrier, it can move those, shuttle those electrons over to the electron transport chain to have this sequential squeezing as part of the electron transport chain. So you can squeeze out the energy from those electrons. So we still have a hydrogen that we need to account for. So 1 hydrogen is going to be used to create a proton gradient. So it's going to be free. So it's just a proton, and it becomes part of what is pumped across the membrane to form a gradient. So when we think about what's what, we need to put in here a bigger statement and write this out in words. So let's think about what happens. Glucose lost electrons. Do we both agree? If you break the bond, as you begin to break down glucose sequentially, when you break a bond, you release, you generate, glucose loses 2 electrons and 2 hydrogens. So glucose lost electrons. when the bond we're talking about was broken. That means that we could use this word instead of writing all of this. We can say glucose was oxidized. Oxidized means loss of electron. So because we're dealing with this handing off, I got it, I'm giving it. Ooh, I got it, I'll give it. Now I have it. Oh, okay, now I have it. This passing along of an electron, you've got to have the proper words, the vocabulary, to speak about the conditions of what this acceptor is in. So, for example, when the acceptor here passes the electron to this acceptor, this acceptor right here that I'm pointing to lost an electron. Now it's in its oxidized state. This acceptor here took the electron, gained it, so it's in its reduced state. So these acceptors have two distinct states. I gained the electron. Oh, I passed along the electron. So we have to be able to speak to what state they're in. So glucose was lost electrons when the bond was broken. It was oxidized. So we never, ever, ever have oxidation without reduction. Who got the electrons? NAD did. So NAD, this is its empty state. It's in its oxidized state. NAD gained the electrons. Right? Gained the electrons from glucose. So NAD was reduced, and because where the electrons go, the hydrogen does too, to form NADH. This is the full bus where it gained the electrons. So this is, as far as this electron carrier, they have two forms. So all electron carriers, acceptors, where they shuttle these electrons, have two forms. So you've got, in this particular case, when NAD, empty bus, it's lost electrons in order to be empty, right? They had to get off the bus. When they did, they went somewhere, and now this bus is missing the electrons. This is the oxidized form. But when we put electrons on the bus, so this bus is empty, it's oxidized form. When it gains the two electrons and the hydrogen that goes with it, gaining electrons converts NAD to its reduced form because it gained electrons, which is NADH. And you have this constant emptying of the bus, filling the bus, emptying the bus, filling the bus. So you can go back from, I have electrons on board. How do I know? Because NADH is the full bus, where it is in the form of its gained electrons with the hydrogen. So right here's your clue. So this is the I have electrons on board bus. And if you lose those two electrons and you lose that hydrogen ion, something else would gain it. So wherever these electrons ended up, that molecule would have been reduced. But since NADH is losing electrons, it's going to go back to its oxidized form. And that's the way this goes, back and forth and back and forth and back and forth. literally think of it, because it's a carrier. It's about transportation. So think bus. So for those of you who are, I mean, everybody's been in this position, but especially like you've been in band and you know how we have the bazillion buses that line up to take you somewhere. We have to really be careful when we think about these two forms, because in this particular case, NAD is missing the electrons. It's given them up somewhere. It's got empty seats. So these are the empty buses that pull up in front of the school. When the electrons get on the bus, okay, kids getting on the big buses, the bus is going to go take those electrons somewhere. It's just as important to empty the bus as it is to fill the bus. There has to be this regeneration of the empty bus. That is crucial. So if you have NAD and you've got electrons, you're going to form NADH, full buses. All the buses can't be full. If all the buses are full and you don't empty the electrons off, you're in trouble, because those buses are shuttles. They go back and forth, pick up the electrons, drop off the electrons, whoop, go back and pick up the electrons, whoop, go drop them off. So there is a shuttle where there's just a big cycle of regeneration from NAD to NADH, full bus, empty the bus. So this would be gain the electrons, lose the electrons. This regeneration of NAD and NADH, forming this right here, is crucial. So that's what's going to drive a lot of these processes, is making sure you have, think about, honestly, if we're going to think about serial killers, is it more important if you keep having serial killers that you have serial killers sitting on a bus and the buses are full? Or if you're still having serial killers made, do you ever want to be without buses? Like, they're all full. Y'all guys are just going to have to be on your own. No, never. Empty buses are the key. Like, this is the key. So of the two, empty buses win the award for most important. So the last thing I want to do is go back over here and make sure we can use these words. They can get confusing. So you even see things like this on some types of like detergent and things. They'll call it, it's an oxidizing agent. So that word means an oxidizing agent is going to cause some other molecule, something else, to be oxidized. So an agent is like, seriously, like a secret agent. It's the same thing. It's the process of causing this to happen. So this thing, this agent, causes oxidizing to happen, causes something else to be oxidized, and it becomes reduced itself. So the best way to think about this, reduction is gain of electron. Oxidizing agents are very reactive. They steal electrons. Because if I cause you to be oxidized, isn't that a really nice way to say, oh man, you lost an electron? No, I didn't lose an electron, you stole it. So oxidizing agents steal electrons. They're very reactive. Reducing agents, you can kind of guess where this is going. We're going to write pretty much the same thing. They cause something else to be reduced, so they cause something else to pick up electrons to gain them, and what that means is, and they become oxidized themselves. So what they really are is they're called electron donors. They're things that readily give up their electrons. So I don't know, other than we just have to say those several times. But the agent is talking about the oxidizing agent. This is the process that it's causing in something else. So reducing agent is causing something else to be reduced. An oxidizing agent is causing something else to be oxidized. All right, so there's that other little half. I think I'm doing pretty good with my time. Proud of myself. Oh, wait. This is what I keep forgetting. So now I'm just going to show you the pages and notes. So for this one, we just had, yep, those 2 pages.